Hello, I'm Paul Beckwith, and I'm going to continue my discussions on the NOAA Arctic Report Card 2018. So I'm talking about surface air temperatures in the Arctic and how the temperature changes in the Arctic temperature amplification is much, much faster than just about any other place on the planet. And this is having profound implications on the global atmospheric circulation patterns, the jet streams, and also on the global ocean circulation patterns, like the Gulf Stream and the overturning overturning circulation systems, the thermohaline circulation systems that basically move water around the planet and are very important for vertical mixing in the oceans. So let me get right into the data from the Arctic Report Card. Okay, I just want to remind you that because the government websites are all inaccessible, if you go to this FTP site, if you type in this URL, then you can get this report that I'm talking about here. So this is showing the map on the left here is showing basically you take a 30-year average, 1981 to 2010, the climo, if you like, the climatology, and you take what's happening in October to December of 2017 and do the subtraction, then this gives you the temperature anomaly relative to this average. Now I should point out that this is not a good average to use, because there was incredible warming between 2000 and 2010. Significant warming between 1990 and 2000. Okay, so these significant warming they're already included in this baseline average. So the average should be much older. We should have from like 1960 to 1990 or something, before there was significant change, or even back earlier to see, how the changes happened. Okay, but the change is accelerating, so we're still getting, huge temperature anomalies, even when we use a baseline, which is not really that good to use. So what we see here on the left is this is the autumn temperature anomalies, if you like. So this is North America over here, and this is Asia over here. We've got Greenland here. Okay, most times you see maps that are oriented differently. They're North American centric. What you have here is, so Alaska's here. You've got the Bering Strait. So you've got huge temperatures above 5 degrees and above average is this dark area here, this dark red color. Anything above 4 is red. The above 3 to 4 Celsius is the oranges, yellows 2 to 3, and so on. So what you can see is very, very warm temperatures just inside the Arctic, inside the Bering Strait. We've got the Pacific Ocean here. So there's a lot of air moving over the Pacific Ocean coming into the Arctic, heating the air. This is air not right at the surface, just above the surface. 925 millibars. Take 1,000 minus 925, you get 75. Multiplied by 10, so it's 750 meters roughly above the surface. And so you get these very, very warm temperatures, and it comes across the Arctic. So, and this is the Atlantic. We've got Iceland, we've got Svalbard. So we've got warm water coming in, warm air coming in, and we get these huge temperature anomalies in the autumn. Also, the sea ice is melted all summer. It's very, very low. The water has warmed up. So come the autumn, it takes time. The air is cooling, but there's a lot of heat escaping out of the ocean water. There's also transport of heat. Like I was saying, there's also a lot less sea ice to reflect the sunlight. So all of these factors lead to very, very huge, large warming, in the autumn time period. Then we go into the winter. So here we are, January through March, and you can compare it to the autumn. And you even get higher temperatures here in the winter, higher temperature anomalies. right over the Bering Strait here between Alaska and Siberia, and also up here. So Svalbard, mean temperatures were 5 degrees or so warmer than normal here. Here they were 7 degrees in the winter. Also lots of melting on Greenland in this area because of the temperature anomaly. Okay, so even larger temperature anomalies in the winter. In fact, the winter is warming much faster than any other month. Okay, so then if we scroll down to here, now we have April to June, we have the spring. So it's only down in this region here that maintains the temperature anomaly near the Bering Strait. And then we go into the summer, and it's pretty neutral in the summer. Okay, now the reason, of course, is pretty clear, is there's still sea ice there, and that sea ice is at 0 degrees. You know, when it's melting, it keeps the temperature at 0 degrees Celsius, right? Heat can be divided into sensible heat, which raises temperature, and latent heat. And when you get a phase change, so in this case we're melting the ice in the summer, the temperature stays close to the freezing point, close to that 0 degrees. Okay, so it doesn't vary, right? But when we lose sea ice, in the regions where there's no sea ice, the temperatures will skyrocket. This is why, as long as there's ice floating on the Arctic Ocean, it will keep the summers like this. As soon as the ice is gone, we're going to see temperatures skyrocketing in the summer. And these anomalies in the summer will be like they are throughout the rest of the year. Okay, so this is the distribution of heat. Okay, it varies a lot depending on the season in the Arctic. Now, if you take the annual mean from October to September of each year from 1900 on, you can get the global, which is the red line here, and then you can get the temperature rise in the Arctic, where the Arctic is defined as anything above 60 degrees. And what you can see is, around the year 2000, there's a break up, and the Arctic temperatures are rising, and these rises are much, much faster than the global average, at least more than double the global average. Okay, and this is north of 60. If you define the Arctic as being from the Arctic Circle up, or from the snow line, or from the 0 degree isotherm, there's lots of other definitions of the Arctic, then the rates of Arctic temperature amplification are even larger than 2 times. Okay, and this is from the chapter called Surface Air Temperature from the Arctic Report Card 2018, starts on page 5. Okay, I talked about the executive summary in the previous video and about the layout and details of the report, also in a previous video. Okay, now also an important thing to look at is the air pressure. Okay, so this can also be reported as the geopotential height. Cold air is heavier than light air. So this is the height that you have to go in the atmosphere in meters, okay, in order to reach a pressure of 700 millibar, which is about 3 kilometers up. Take 1,000 minus 700, that's 300 multiplied by 10, it's about 3,000 meters. Okay, the pressure drops pretty linearly, at least near the surface, and then it goes up, non-linearly. But you can estimate that's about 3,000 meters, normally 3,000 meters, so it's normally somewhere in the middle here. Okay, so if the air is very, very cold, be high pressure. So the level of the pressure will the air is compressed. For it to be 700 millibar, you don't have to be so far above the surface when the air is very cold. So the pressure is low here. So what we get is almost like a trimodal pattern. Okay, we get one low pressure, we get a second low pressure, we get a third low pressure. Now what happens is the air has to be higher outside. The air moves into the low pressure, it deflects to the right in the northern hemisphere. So this is the motion of the air. So look what that does. It brings cold air down to North America, and it brings warm air over the oceans up into the Arctic. Over here, the motion of the air around this low pressure cyclone will always be counterclockwise. So it brings warm air up into Alaska, from the ocean up into Alaska, up through the Bering Strait, cold air over here. And this minima here, it will do the same thing. It'll bring cold air down to here and warm air up into the Arctic. So lo and behold, if you go back to this plot here, you can see these cold areas here, here, and here. And this is because of the circulation, right? Warm air comes up there, cold air comes down here. This cycle is here, cold air down here, warm air up into the Arctic, and the same thing here. Okay, so that's the way that works. So if we go back down to the other months, this is February of 2018 here. Okay, and you can see this massive cold area, this massive pressure low. So a huge flow here of air, warm air up into the Arctic, cold air over North America. Same thing over here. So back here, okay, the cold air is driven down into Europe, making very, very uncomfortably low temperatures throughout all of Europe. Okay, well, this guy here brought the low pressure here, brought cold air down here into Europe and across, cold air into, Asia here. Okay, so this is 2 lobes here. This is like 3, wave number 3, or 3 lobes, trilobal, trinodal, binodal here, 2 nodes. Okay, in February. And then if we go down here, this is March. You can see the pressure low over here. And here, there's a very weak pressure low over the Arctic. Now, because the air is now, when there's lots of sea ice, the cold air is above it, okay, and that air is dense and it moves outward, deflects to the right because of the Coriolis force, okay, and it drives the Beaufort gyre and the transpolar drift. And now we have a low pressure here, okay, so the air moves in, goes this way instead. So it reverses the Beaufort gyre, if you like, and it brings the transpolar drift is the opposite direction, and that brings warm, salty water from the Atlantic into the Arctic. So you might hear the term Atlantification of the Arctic Ocean. Okay, this is what's happening. The land is much, much warmer than normal. So the lake ice is melting, the rivers are flowing all into the Arctic. They're bringing fresh water into the Arctic. But meanwhile, there's a lot of advection of seawater from the Pacific in and the Atlantic in, and this is bringing a lot of salty water in, which makes it harder for the ice to refreeze in the autumn months. Okay, so basically that's the nitty-gritty, the nuts and bolts of the Arctic. Okay, so I would expect this pattern to continue, in fact, be more amplified in the next few years. Okay, so the 2019 report, Arctic Assessment 2019, 2020, and then boom, okay, we're going to lose Arctic sea ice by the end of the melt season. So what will happen is, say it's gone for all of September, well, the temperatures will start to really get a lot warmer in the Arctic in September, no sea ice. So it'll be harder to form, and then the next year, there might be no sea ice for August, September, October, and then a few years later, July, August, September, October, November, no sea ice at all in the Arctic. So then the patterns in the summer months will be quite different. We won't be neutral anymore. Okay, it will be bright red here. The temperature anomalies will skyrocket, and the jet streams will become even more distorted, and everybody will be talking about the Arctic because with no sea ice, extreme weather events are going to greatly increase around the planet, and it's going to be much, much harder to grow food. There'll be a lot more failures of crops, and food prices will go up significantly, and then everybody will be panicking about abrupt climate change. So I want to thank you.